Hello students, in this video we will get a little bit more into orthogonal projections and we will try to understand how we can project any vector on general subspaces. In our last video we understood how we can represent a vector in n-dimensional vector space onto a line by taking orthogonal projections, and we also learned that the reason behind orthogonality is that it would ensure that the loss or the compression loss is minimal. However, now let us extend our discussion to more abstract notation. That is, let us say that we have a vector x, which is an n-dimensional vector space, and there is a subspace of U, which is subspace of n-dimensional vector space, and we want to project our vector x onto subspace U. And this dimension of U is equal to m, which is greater than equal to 1, and of course since this is subspace of n dimensional vector space, the upper limit of m is equal to n. Now there is a vector which is represented, as we said, in n dimensional vector space, and if this is a u, the dimension of u is m, that would mean that all vectors in this subspace can be represented by the bases b1 b2 all the way till m. And idea is how we can project this x into b1 b2 and so on. Now we are denoting this representation of projections by pi of x under consideration, and we can project this pi of x on lower dimensional vector space. That would mean that now this can be written as a linear combination of lambda 1 b1 plus lambda 2 b2 plus lambda 3 b3 all the way till lambda m bm. And in compact notation we can always write it as B matrix, where B comprises of b1 vector, b2 vector, b3 vector and so on, multiply by lambda vector, where lambda vector comprises of lambda 1 lambda 2 all the way till lambda n, and here this is b1, this is b2 all the way till bm, and when we multiply these two we end up with the same result. Now we learned that when we take the geometric interpretation, that is, there is a vector x and we want to project it on a line which is spanned by the basis b, and we were saying that whatever projection we take, that should be orthogonal to b vector so that the compression loss is minimal. So this would be given by x vector minus so this would be our, up to this point is pi x, and hence this vertical distance can be represented by x minus pi x, where this is the projection. Now in the case of this general subspaces, we would make sure that whenever we are taking the projections with respect to these m bases, this condition of orthogonality is still preserved. That is, we can still write that the inner product of b1 and x minus pi x is still equal to 0. Inner product of bm x minus pi x is equal to 0. And when we take the specific case where we replace the inner product by dot product, and that would mean our transformation matrix becomes an identity matrix. So this would become our dot product. We can always write this as the product between b1 transpose multiplied by x minus the projection of x onto the m dimensional subspace, that has to be equal to 0. Also, we just saw that in compact form we can always write it as b lambda. Hence, substituting it here, we can write this as b1 t x minus b lambda equal to 0. Even for the other vectors, since we are saying that projection or the difference of original vector and the projection when multiplied by individual bases should be equal to 0 for the condition of the orthonormality or orthogonality, we can write this as b2 transpose x minus b times lambda equal to 0 all the way till bm transpose x minus b lambda equal to 0. And when we have to write this in the compact form, we can again say that this is the collection of b transpose multiply by x vector minus b lambda equal to 0. And now we will solve this simple algebraic equation where we say that this is b transpose x minus b transpose b lambda equal to 0, which can be written as b transpose x equal to b transpose b lambda. And if we take inverse of this on both sides, we can say that B transpose B inverse BTX vector equal to lambda vector. So as soon as we know this lambda vector, we know that if we multiply this lambda with the original vector x, we are essentially talking about the projection of x onto a lower dimensional vector space, or in this case the vector subspace. Now let us try to understand this with help of an example. Let us say we are given an x vector which is represented by 3 1 0, and as you can see that it belongs to three-dimensional vector space. We want to project it to a two-dimension subspace which is denoted by u equal to, where u is spanned by 0 1 0 0 and 0 1 0. So that is the, now the span of u is just two dimensions because there are two columns in basis of u, and we say that span is, it becomes basis when these two columns are independent, which is rightly so in this particular case. And now the question is how we can do this projection of x onto a lower dimensional space. Now in this case we can write our b as 1 0 0 0 1 0, and B transpose in this case would become 1 0 0 0 1 0, and hence we can easily go back and calculate B transpose B, which would be of dimension. So this is now 2 cross 3 multiplied by another vector of size 3 cross 2. It would be simply 2 cross 2. Since this is a square matrix and assuming that this is invertible, which is true in this case, we can always calculate B transpose B inverse. And in this case, you would see that since both of these 1 0 0 0 1 0, they are orthogonal to each other, this B transpose B comes out to be an identity matrix, and hence its inverse is also identity matrix. Then we again multiply it by B transpose. So this dimension here comes out to be 2 cross 2 multiplied by 2 cross 3, and the resultant of this is 2 cross 3, and when we multiply it by the vector x, which is our original vector that we want to project, which is of dimension 3 cross 1 as it belongs to R cube, our output comes out to be of size 2 cross 1, and hence we can project a vector which was in a three-dimensional vector space to a two-dimensional subspace. And this is one example that we would frequently use whenever we have to reduce the dimensions of a vector, but we will do it in little bit more sophisticated way where orthogonal projections would be used more intelligently to minimize certain losses, and we will talk about those losses in next couple of videos. Thank you.